How we do, guys?
Sunshine.
Questions about any of those?
Can you explain B?
Which one?
B.
B,
Yes.
making an epoxide. Here's your epoxide,
Mm-hmm.
plus enantiomer. Explain what part. MTPVA is a peroxy acid.
Okay.
What does a peroxy acid do to an alkene? Makes epoxide. So you can draw epoxide, and in stereochemistry, is the oxygen, 2 bonds to oxygen, going to be cis or trans? They're going to be cis. Here's your alkene.
Mm-hmm.
It's planar, it's got a face. Here's the alkene if it's like this. Peroxy acid is up here. The alkene attacks the oxygen.
Mm-hmm.
And to get an NAF cation, what does the oxygen immediately do? Back bonds. First bond's up, back bond, the second bond has got to also be up. They're both up.
Okay.
But it can also be both down. I would be more interested, what did you put?
So I bonded oxygen with CH2.
What do you mean CH2?
So where the oxygen is, I thought it's oxygen will bond to CH2, the methyl.
Okay. Well, what does a peroxy acid do to an alkene? Makes an epoxide. Boom. Okay. All your reactions, you got to have a beginnings just statement, a little bit of memorization, yeah. Okay. No carb. All right. What do you get when you react an alkene with halogen and water? Halohydrin. Yes. Boom. 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 What does a halohydrogen look like? What does an epoxide look like? Boom. Boom. Ultimately, then probably you'll then finally assess stereochemistry.
Could you explain number 4, please?
Number 4, which of the following is stereogenic? This compound has no stereochemistry. There's nothing possible. It means it's not stereogenic. Stereogenic means it gives rise to stereochemistry. This compound, there is no stereochemistry. That is, you cannot draw it in any multiple ways. There is neither is the one on the end. This one, yes, as drawn, these groups are cis on the alkene, but we can also draw them trans. So this compound has stereochemistry. That is, the way it's put together leads to stereochemistry. That's what stereogenic means.
So on the third one, like you can't move the alkene to the top, and that would be the same thing. Like
It would be the same thing.
but you can't do that. That's not called stereogenic.
But it would be the same thing, like you said. If it's the same thing, it's not a sterilizer. It's the same thing. You do recognize it would be the same thing, which is good, but that's not stereochemistry. Okay, mechanism. Alkene attacks H+, give this cation. We really need cation here. We can envision a methyl shift to give cation here. Methanol electrons add here. Give this, and then something takes the H to go neutral. You can use the bisulfate. Usually don't require you to draw the structure out, or you can use water to pick it up. Because how does this really exist in water? H3O+. We've said that numerous times. Okay, guys, check it out. He will be posted upstairs. Lab this week. Any questions? The lab from last week. Your answer sheet will be due to, in lab this week. Okay. The bromination lab you'll be doing, that is a report. I think we just meet upstairs this week. Okay, let's see where we're at. Alkenes. We need to move along with our reactions. We were looking at outline, yeah. Last time we looked at oxymercuration reduction. We also looked at hydroboration, oxidation. These are two ways to get alcohols. They're complementary. One gives the Markovnikov product, the typical product. One gives the non-Markovnikov or atypical product. You understand what's going on with that terminology?
Will anything other than peroxide give the anti-Markovnikov?
Anything other than peroxide?
Give the anti-Markovnikov? So should that just be a red flag to us that that's going to produce that anti-Markovnikov, the non-Markovnikov?
Yes, when you see borane followed by hydrogen peroxide, that's a red flag. That is non-Markovnikov hydration. Okay, we have our outline. We ended a little quickly last time. Let's go back and look at hydroboration, which is, we've got a number of predicted products below on each sheet. We'll eventually come back and be looking at those. I expect that you'll be working on those and asking questions. So when you do look at them, you'll be ready to learn from those. Hydroboration. Any questions about the mechanisms on these two pages? Any questions?
How do you know, like how many voltages is on that?
I said that. I said it's a little bit hard to tell, but at least has one. Otherwise, we'd have to really look at the periodic table. But I just kind of told you, at least has one. At least has one. Okay, let's see how we did on this here. pH 3 followed by hydrogen peroxide. First off, what does this do to an alkene?
First on same thing she was asking, it was, once when it back bonded, that mercury also back bonded, how did the, what did the OAC or the acetate never move off of the mercury, or did it move on off of the back bond? Is that what happened? Because at one point we only had the mercury, and the other point we had the next mechanism we had hold of. And I don't see how we got there.
Either I left it off or you left it off on your paper.
Maybe I did. Was it supposed to, like,
No, that should have a mercury acetate
Okay.
sitting with it.
okay.
Okay, how do we do on this one down here? First off, yeah, what does this do to an alkene? Anti-Markovnikov hydration. Okay, we can draw our product with no stereochemistry. What's the product going to be? There you go. How do we get to that point? Well, books will tell you that so-and-so ends up on the least substituted carbon, or the H ends up here, whatever the books say. But what have we been saying? Okay, where would you make cation at? Top or bottom? Top. And if you're doing a hydration, what adds to the cation ultimately? Maybe not exactly here, but water, right? I mean, the OH adds to the cation. That's our initial thinking. But we know that this gives the atypical. So instead of the oxygen bonding to where the cation would be, it miraculously ends up bonded to the other carbon. That's the atypical part. That's just sort of your starting point. A little bit of memorization, yeah? Okay? And thus we can put the OH here, and there's actually a new H there. Because over here, there's no H there. And we have ultimately added water to this alkene. And we've ultimately thus hydrated it. Now, we didn't react it with pure water, or with just aqueous acid. We reacted it with some kind of convoluted, crazy reagents. But ultimately, we hydrated the alkene. There's your product with no stereochemistry. That's the regiochemistry. That is, we have the things bonded to the right regions. Now again, your book will say that the H ends up on somewhere.
Plus.
Again, I'm doing it consistent every day, how I would tell you. But what's the stereochemistry? Well, first off, does this product have any? Or is the question moot? Yes. Well, these two groups can be cis or trans. Rings, two groups, cis or trans. Are they going to be cis or trans? They're going to be trans. They're going to be trans. We'll explain why. It's all in the mechanism. Now, since I showed this trans, let's continue. Let's think further about stereochemistry. Is there another way to show trans? That is, can I further consider stereochemistry? Yes. Let me ask you this. Does this structure have an enantiomer? Is that structure chiral? How do you tell?
Carbon.
That's one way. What's the broader way? How do you tell if a compound is chiral? Look for a plane of symmetry. Where's Waldo? Can you find a plane of symmetry? No. There is no plane of symmetry. That tells us that the mirror image will be an enantiomer. It has an enantiomer plus an enantiomer. That's how books will maybe show this. Well, what does the enantiomer look like? That's where everything is reversed. All these terms, okay? You can keep check. How many times have we said this? Everything's reversed. That is, make this like this and make this like this. That is the enantiomer. Because if you do R and S, whatever this is, that's the other. For example, if that's this down here, if that's S, then that's going to be R. Or vice versa. That's the enantiomer. But the enantiomer is also trans. Because if you ever go look in the mirror and you hold one arm here and the leg back, trans, opposite, your mirror image better also be like that. If your mirror image has that, cis, you got a problem with your mirror. The mirror image of trans is trans. Okay, well, why trans? First off, trans is a relative term. When we say relative, we're talking about two groups, their orientation to each other. They're trans to each other. We do not get cis. Why? What's going on here? Well, let's think about mechanism. Here's the alkene. It attacks the boron, correct? Here's the boron coming around. Alkene's like, ooh, empty orbital. Okay? So it attacks the boron. Let's draw this. This comes and attacks the boron this way. It pulls away here, attacks the boron. So the boron is going to be bonded here. I'm going to draw it. When it's bonded here, this is now tetrahedral because it takes on another bond. It's got to either be forward or back. Let's draw forward. B, H, H, H. That becomes minus. And this is cation up here. Okay? We know this is NAF because what's the next step that happens at the same exact time? One of these H's gets, like a hydride shift, it gets thrown over here by the boron.
So hydrogen shifts can happen more, they don't have to be right next to, right? Or is it just in this time?
This is a 1, 2, 3 hydride shift. Before we were doing 1, 2 hydride shift. Okay? Now, if you want to make it look a little bit, we can have it a little closer. Okay. Boom. This comes here. NAF. This happens at the same exact time as this is happening. This is all going on. What does that give? Now if the boron is now becomes BH2 after it gets rid of the H, this is now tetrahedral up here with 4 things. How is the H projected? Here's the answer. Because it came from the boron, the H has to also be forward. Because look, you're the boron with the H's. I attack you, so my bond's forward. Now you throw an H at the other carbon and keep your bond there. There's the H bond. It's also forward. It has to be. How can it be opposite? You're going to throw a curveball and come around from back here? No. The H is forward because it came from the boron, which was forward. Since the H is forward, how's the methyl now?
It's in the back.
Back. It gets pushed back. It's now tetrahedral. It's got to be... There you go. There's your hydroboration product. What does the magic step do? The magic step, as we said, replaces the BH2 with what? OH. And what else did we say? We made a comment. No change in stereochemistry. Just erase it and make it OH. That's the magic. There's your product. And that's that right there. Now, we usually don't draw in H's, right? So let's just get rid of that. You see? It's trans. Now, how do you get the other one, the other trans? Instead of, back here at the original, instead of the alkene attacking the boron forward, maybe you're sitting over here and the boron attacks it back. And you got a 50-50 chance in the chemical world. If it attacks it back, that's back. And if it's back, how's the H bond going to be when it's thrown in? It would also have to be back because it comes from the boron. So that's why you get trans. But you get both because it can happen from both sides, and that leads to both. And as we've said, all reactions we're doing right now, until we say differently, are going to give both enantiomers when possible, when there is an enantiomer. Do we now understand why the product is trans?
Yes.
It all comes from your mechanism. All your stereochemistry comes from your mechanism. The one on the quiz with the halogen in the water, okay? It's all mechanism. That's why we learn the mechanism, both to help us predict just the regiochemistry, where things are going to be attached, but also the stereochemistry. Okay, one below. Anybody got a product for the one below? What does this do to an alkene? Hydration. Standard or non-standard? A Markovnikov. Yeah? Anybody got a product? Anybody got a product? Including stereochemistry? A stereochemistry assessment? There you go. There's your product. End of discussion. That is a 6-membered ring, right? I mean, I don't know what this is. But, all right, I can't draw 6 members. Right? Yeah? Is that not right? Any stereochemistry here? Is it chiral? No. Do you have relative stereochemistry? Do you have cis-trans possible or something like that? No. Game over. There's nothing to consider. There's no other way to draw it. Yes, that's tetrahedral. You can show the OH forward and the methyl back, or you can show the methyl forward and the OH back. Guess what? That's the same compound. So why show it two different ways? Usually we just keep it generic because you don't need the precision. Yeah? Okay, two very important alkene reactions. Applications. There's an exact procedure. Organic syntheses, if you're not familiar with this, it used to be a yearly serial that you had to pay for. Now it's free online. Wow. All types of chemistry. Exact procedures. So if you want to read exact procedures, see experimental details, that's a good resource. Here's a reaction that does a oxymercuration followed by reduction. They produce mercury metal, like we said. Over here is a drug synthesis. And variety of reactions that we'll see along the way, either in this class or in Organic 2. Right here, though, what are they doing? It's a hydroboration oxidation. 9-BBN is a more sophisticated variation of BH3. If you ever see 9-BBN, just mark it out and do this, all right? But you guys would probably never see 9-BBN. So, what does this do to an alkene? That's okay. Now, first off, that's a diene, got a little bit of reactivity. The chemistry is taking place here, this, if you look. Okay, here's your alkene. Where is the OH going to end up being bonded, top or bottom?
Top, because it's 8.
It's actually top. Because the cation would be down below. Okay, so you got to get that thinking, okay? That's your starting point. OH up here. Indeed, the OH is up there. They have done a hydroboration oxidation to give. They hydrated the alkene to give this alcohol. So if you want to see an example of how it's being used, there you go. You can also see a little bit of research. If you read the article or the paper, they're trying to improve this step. To do it, they do a little study. They use different borane reagents. They use BH3. By the way, BH3 usually has a friend with it. Here, THF is sort of a solvent. You see, BH3, the boron does not have an octet. Because of that, it's missing electrons. And so things with electrons really like to be there with it. It's almost as if this was positive. And if you have a positive, you got to have a what? Negative. If you got an empty orbital, you're usually going to have, there's usually going to be something there that's filling that orbital. Okay, you can look into it. But that's why you usually have a complex. And usually I don't really show that, but you guys may actually see this. Okay? The main thing here is the BH3. Then they tried 9-BBN, different conditions. They did these at room temperature, and then they did this same reagent. They did a little heat. And then they looked at some yield. If you're interested in your experimental, you can take a look at that. Try to get the best yield. Okay, let's see where we're at. I think we made it around the circle there. We made it all the way around, yeah? When you first saw this, it probably looked intimidating. Doable now? Consistencies? We showed it trans there, by the way. Hopefully now you can understand why. Let's look below. We got a couple more reactions to look at with alkenes. Really maybe only one, because this is... All right, here's another one. Reaction with just H2. In lab this week, you're reacting with Br2. And what happens? You end up with a Br on each carbon of the alkene. But with H2, you end up with an H on each carbon of the alkene. H2 is called hydrogen, and so we are doing a hydrogenation of the alkene. Also, when you add H's, that's known as a reduction. So you can also call it a reduction of the alkene. Now, this is kind of simplifying the alkene. When you add H to each carbon, you actually end up with what? What type of product? Not alkene, but alkene. You turn the alkene into an alkane.
Is that precious metal typically platinum?
Platinum, palladium, nickel. Nickel is not as precious as the others. Some of them should be noted on the next page. You can also have some very sophisticated ones like iridium, rhodium. Those are even more precious. This is opposed to the non-precious ones like iron and zinc, which usually do not work here, unless they're very sophisticated somehow, complex. Okay, we're also going to have some stereochemistry to consider. For example, if you hydrogenate this alkene to this alkane, the two existing groups will end up cis to each other. Where over here, you would not say that these are cis or trans, because here everything is in the plane. There is no forward or back here, because these are planar carbons. But now the carbons are tetrahedral, because now we have two new H's, right? Did we have to draw them in? We knew there were two new H's here, right? Because that's what we're doing. We're adding an H to each carbon. Okay, mechanism for this is on the next page. So it's back over here on our... All right, we're not going to be doing a full arrow pushing mechanism for this. It's a syn addition of H2. Syn meaning cis. This means the same side. Okay? What is sort of known here, again, no arrow pushing really. But I'm just saying it, instead of just saying pure magic, we're going to kind of look at some detail. The alkene, with the pi bond, approaches the metal surface. Well, also the hydrogen sort of absorbs to the metal surface. And then here's where it gets a little bit fuzzy, and I don't think the exact details are known. But through the interaction of the hydrogen with the metal surface, the hydrogens become almost, okay, let's oversimplify. You know, they almost become separated and then like darts. And two H's are then shot into the pi system. And that's what this is trying to illustrate. Off of the metal surface, and the two H's end up there. Okay? Wow, what did he just say? I told you, it's very kind of vague. If you want more details, you have to go hunt for it. But here's the important part. We have an alkene. Where'd my alkene go? I lost it. I'll make another one. Here's the alkene, okay? You're the metal surface, and the H's are there, and they become like darts, so they associated with you, and something happened there. Okay? Okay? Now, boom. Boom, they're in. Make bonds. One to each, okay? The two H's are on the same side. Well, they came from the same side. They came from the metal. One doesn't come here, and the other one magically come in over here. They come from the metal. That's why the H's are on the same side. So, it's called a syn addition. And we'll look at this example first. You take this alkene, and then two H's come from the same side. What does that do to the two existing groups?
Pushes them back.
This is where both H's came from the back. It pushes the two existing groups forward. So they end up being cis. Why are they cis? Because the H's are cis. Why are the H's cis? Well, they came from the metal. Okay? And you would only get a cis product. You're not going to magically do this reaction and have these two groups trans to each other. It's a syn addition of H2. Now, of course, we can sometimes see the isotope of hydrogen, and you might see D2 here. Okay, what are the precious metal catalysts? We've sort of already mentioned that. Over here, we can look at this example. You take this compound. What's the name of this compound? 1, 2, 3, 4, 5.
Pentane.
1 pentene.
Pentane.
1 pentene. Is that it? Is that definitive, or do we need stereochemistry here? Is this compound stereogenic? No, it's not. There's no stereochemistry. Game over. 1 pentene. If you hydrogenate 1 pentene with hydrogen, and one of these, I had a student one time thought that you had to use all of these. It's only one. Your choice. Palladium and nickel are probably the most common that you'll see. What do? H to each carbon. That actually just gives the alkene, right? There's an H on each new carbon. New H on each carbon. And they just give pentane. By the way, nobody's out there making pentane this way. Because pentane comes from petroleum. Usually you take pentane and you want to get to this point, something a little more sophisticated, then you can move on. Because when you get to this point, now you can make epoxides, you can brominate, you can do all things. You can't do much here, so usually you're going backwards. We'll see when you would want to use this reaction along the way. Look at this. Both of these reactions, what is this here? This is 1, 2, 3, 4, this is what, 2 pentene? Do we need any descriptor in front of this one? Yes, this is E, right? E 2 pentene? Or trans? Everybody watch the video on nomenclature? I don't believe it, because I know the view number.
This is the same.
Do what?
This is the same.
No, these are not the same side. These are
No,
opposite.
I'm just saying what that was your
No, this is E.
your clincher in the video.
But of course, you could also have Z. If you hydrogenate this, you actually also get the same product. Please recognize that. Or if you hydrogenated Z, it would give the same product. All things here lead to pentane. So, question though. Which reaction would be more exothermic? This or this? Hold on, first off. Why exothermic? Why didn't I say which would be more endothermic? Are these reactions exothermic, would you think? You can get your calculator out, but we will go back to a calculator at some point, or maybe not. Depends on if you need to.
It's because you're breaking those double.
Breaking a carbon-carbon double bond.
Pi bond, we're breaking a pi bond. What are we forming? Two stronger sigmas. Sounds like, I bet you, steak dinner, that your calculation will show this is exothermic. Okay. But which is more exothermic? Top or bottom? Let's graph this. Okay. Alkene. A, B, C. They're both going to C, right? You know the axes. Please label your axes. C. Okay. A and B, are they the same or different? Obviously they're different. They're also both higher than C. So we put A, one here and one here. They're a little bit different. Are they? Are A and B different in terms of their inherent energy? Which one's more stable, A or B?
B.
B. Do you know that, right? So B should be lower. Correct? Okay. Is there any intermediate in here? Did we show an intermediate? No. The reaction is just this transition state. The transition state is shoot some H's in. You see the transition state where they're coming in? That was the high energy. He had to move his arms up. I had to come over here closer. That all took a little energy. This one here, at some point along the way, these sort of become the same. They end up the same. Which is more exothermic? A to C or B to C? Well, this goes from here to here. This goes from here to here. Which one drops more? Which one gives off more energy? A. Which one's more exothermic? This. No, that's not A. A is more exothermic. A. The top. Mainly because this alkene had more energy to give off. Plotting things, doing it, okay, instead of just thinking in your head, plot it out, analyze it. Make it simple. Jump it up in your head, that ain't simple. You guys tend to want to do that though. I tend to want to give you a process of thinking. Let's see what else is here. We also have our outline. Basically, there's also a couple of applications. There's a couple of questions on the next page. Please be looking. We'll quickly finish this up, and we'll be moving on to stereochemistry next time. Starting where we kind of left off from the lab lecture.